Hello everyone, this is problem C of Educational Codeforces round 150. So in this problem, we are assigned some values for the characters from A to E. So for these 5 characters, we are assigned some value. Let's call them P of the character. So P of A is equal to 1, P of B is equal to 10, for C it is 100, for D it is 1000, for E this is 10,000. So we are assigned these values for the characters from A to E, and we are also given a string. In the input we are given a string. The value of this string will be the sum of the values of the characters. So let's say a string is AB, AAC. So the value of this string will be the sum of the values of the characters, but these values are signed. So for a character, if there exists a greater character in front of it, then the contribution of this character will be negative. But this doesn't have a greater value in front of it, so the contribution for this will be positive. But if we take a look at this character, this has a greater value, a greater character, which is C. So the contribution for this A will be negative via A. So this way we're going to calculate the value of this whole string, and for this problem we can change at most one character of the string. So if this is the given string, we can change at most one character of it. So by changing at most one character, we need to find the maximum value of this string calculated in this way. So the size of the string can be up to 20 to 10 to the power 5. So this problem can be solved using a pretty easy dynamic programming approach. So let's say this is the given string, and we're going to run a DP on it, and the states of the DP are going to be the index, the current index, the maximum value, the maximum character that has occurred up to here. So we're going to start the DP from the last index and go to the first index. So we can keep a state which will state the maximum character that we have found up to now. So the max value, and we're going to store another state that is going to denote if we have changed any character or not. So it is going to be a 0 or 1 state, and this is going to denote if we have changed any character or not. So what are the transitions? Let's say we're at this index, and let's say the character of this index is C, and there are two options. We can change C or we can not change C. So change and not change. So let's take a look at not change first. If we do not want to change this character, then simply the value for this position will be V of C, and it will be multiplied by -1 if there exists a greater character than C in front of it. And the max value state will give us that. We're going to compare the max value state with the current character C. If max value is greater, then we're going to get minus V of C, and if it is not greater, then we're going to get plus V of C. So this is what happens if we do not change the current character. But if we want to change the current character, there are some conditions. The changed state needs to be 0, because if we changed a character before it, we cannot change the current character. But if we didn't change it, then we can change the current character. So if the value of the changed state is 0, then we can change the current character, and we can change the current character into any one of the 5 characters that are given, so A through E. So we can check all these possible characters to change the current character into, and let's say we want to change the current character into B. Then we're going to compare this B with the max value state. If the max value is greater, then we're going to get minus P of B. and if it is not, then we're going to get plus b of. So in this way you can calculate the maximum sum using dynamic programming. So let's take a look at the code. So we take the string in input and we need to reset the dp array using -1s. Then we just call the solve function at this state. So let's take a look at the function first. So the function has three parameters. The first parameter is the index, the second parameter is the maximum value, and as I said, the third parameter is going to be if we changed a character or not. So we're going to call the solve function from the n-1th index, and at first we do not have any character, so the maximum value can stay 0 and the changed variable will be 0 because we didn't change any characters. So inside the solve function, if it is the base case, if the index is -1, then we return 0. If the dp value is not -1, then we return the dp value. Otherwise, for the current character, if we do not want to change the current character, then I'm checking the sign for this character. If the current character is less than the maximum character, then the sign will be -1. So then this is for the case when we do not want to change the current character. So the result will be sign times the value of this character, and we're going to call the solve function in the previous index. So solve in -1 and the maximum among the maximum up to here and the current character, and the change will remain the same. And now if we want to change the current character, the change state needs to be 0. We need to check it at first. Then we can change the current character into one of the 5 possible characters. So we run a loop from 0 to 4, and if this character is not equal to the current character, then we can change it. So we calculate the sign for it in the same way, and we also take the maximum value in the result variable. So the sign times value of I plus we're going to call solve in the previous index. The maximum value will be changed. If it is changed, it will be changed by maximum, mx and I, and the change state is going to become 1 now. And after we're done with this, we're going to just return the maximum value that we got for this state. Yeah. So this was problem C. This is problem D. So in this problem, we're given an array of segments. So we're given some segments in the number line like this, and an array of segments will be called beautiful if the size of the array is k, where k is even, and for each of the segments there exists exactly one other segment that this segment intersects with. So if this was the given array, this would be called beautiful because there are 4 segments. So 2 segments here and 2 segments here, and this segment intersect with this one, and this segment intersects with this one only. So no segment intersects with more than one segment, and each segment intersects with one other segment. So this will be called a beautiful array. So we're given an array of segments, and we need to find out the minimum number of segments to remove so that the given array becomes beautiful. So for this array, we can remove this segment and this segment. So if we remove these 2 segments, then we're left with this array, and this is beautiful. So the answer for this will be 2. Okay. So let's draw the segments again. So what we can do is we can find out the number of the maximum number of segments in a beautiful array, and then subtract that value from n to find the minimum number of segments that we need to remove. So for this array, we can find out the maximum number of segments that can stay to make the array beautiful. So these two segments and these two segments can stay to make the array beautiful. So we're going to get the value 4, and if we subtract this from the value n, then we're going to get the answer. So this is what we're going to do. And how are we going to do it? We're going to use dynamic programming to solve this problem. So at first, let's sort all the segments. So segments are like this, Li and Ri. So let's sort all the segments on the basis of Li. So if we sort all the segments, then the indices will be 1, 2, 3, 4, 5, and 6. Yeah. So now we're going to run a dynamic programming where the state will hold the current index of the segment that we're at. So at first we can stay at this index 1. So what we're going to try to find out is which index or which segment we're going to pair up with the current segment. So we can run a loop from 2 to 5, 2 to 6. So as the current index is 1, we're going to run a loop from 2 to n, and for all these segments we're going to check if the current segment 1 intersects with that one or not. So for 1 we can check with index 2, and these two intersect. So these two can be stored in a pair. So we're going to try all these possibilities. So we're going to run a loop here and check if the current segment intersects with the, let's say this is j, intersects with the jth segment or not. So here is one possibility. We're going to pair 1 with 2. So if we pair 1 with 2, then the next segment that can start, it can start after the end of the second segment. But if these two segments were like this, so this is 1 and this was 2, then the next pair that can start is after the end of the first segment. So for the two segments that were intersecting, we're going to check the maximum value of Ri, and the next pair can start after that value, the maximum value of Ri. So this is what we're going to do. So we're pairing I with j. Then we're going to call the solve function on the first index, that is after the maximum value of Ri of these two indices. So the max of Ri and Rj plus 1. The next segments can start from this value or any larger value. So we can calculate this using a binary search, as we have sorted the arrays based on Li. So we're going to calculate this value and we're going to run a binary search to find the first index that satisfies this, that is greater than or equal to this value, and then we can call the solve function in that index, and we can check the same thing starting from that index. So then what is going to be the complexity? We have one state, that is the index, and we're running a loop in it. So index can be up to n. We're running a loop that can be up to n, and we're also running a binary search that will be log of n. So the total complexity will be O of n square log n. As the value of n is up to 2000, I think. Yeah, the value of n is 2000. So this will obviously work. So let's take a look at the code. So at first, we're going to take all the ranges in input. We're going to sort all these ranges, and we need to reset the DP array with -1s. Then we're going to call the solve function from index 0. And in the solve function, if it is a base case, if the index is greater than or equal to n, then we return 0. If the DP value of this index is not -1, then we can return the DP value. Otherwise, there are two ways. We can include the current index, the current range in a pair, and we cannot include the current range in a pair. So this is at first to check uh, what is going to be the maximum value if we do not include this current range in a pair. So then we can just call the solve function in the next index. But if we do want to include this range in a pair, that is when we're going to run a loop from n plus 1 up to n minus 1, and we're going to check if the current range and the jth range intersect or not. So I wrote a separate function to check if these two indices, if these two ranges intersect or not. So this is going to give me that value, and if they intersect, then they can be stored in a pair. So we need to find the next index in which we can start checking from to find the next pair. So that is what we're doing. So we're going to check the maximum value of the R of these two indices. So a in dot second and a j dot second, and we're going to find the upper bound in the A array of this mx value. So we can call the solve function starting from the index. So we're going to do that. We're going to set res equal to max res. This 2 is for the pair that we formed right now, and we're going to call the solve function into the index. And then finally we can just return the maximum value that we found for this state. So this was problem D.